I hope all is well with everyone. This is Celestial Navigation on the Flat Earth, Episode 4, Intro to the Stars. We have showed previously that the Gleason's Flat Earth map is a longitude and time calculator, as stated on the map. We have showed that it is literally acting as a clock, and this is the Sun, Moon, and Zodiac Clock app. Check it out if you want to learn more. And we figure the longitudes by using the Greenwich hour angle, which is the longitude that cuts through Greenwich, UK, represented by that black line there. So we showed that we get a GHA for the sun, which is Greenwich hour angle, and a declination. Okay, I went over that. So for people who hadn't seen it, I'll just brush up. So the declination's for latitude, and that black line represents the zero longitude. So if your GHA for the sun is 15 degrees, then it's 15 degrees off zero. And you see there's 24 zones of longitude representing the 24 hours of the clock. So if GHA for the sun is 15 degrees, then move over one segment. It's pretty self-explanatory. Now the stars are a little bit different. You see Aries, you see all it gives is a GHA. It doesn't give declination because it is a fictitious spot in the sky. It represents the position of the sun at the beginning of vernal equinox, and it moves around. And all the other stars, you just get a chart and you get a sidereal hour angle, or SHA, which it's pretty easy. Here's the list of the stars, and it is just their position compared to the rotating GHA of Aries. So in essence, all you do is you locate the longitude for Aries according to the GHA, and then whatever the chart says, the star chart, the SHA, you just add it and circle your way around. They're going to tell you some bullshit math, when to add and subtract. You don't have to do that. Just add to the GHA and just circle it on around on a flat Earth map. It's nothing tricky about it. Everything is easier on the flat Earth map. So I'll give a quick example. So let's say we go to Aries, okay? We get our day and our hour, and we go to the chart. We look at Aries. Let's say it said 15 degrees GHA. So what we'll do, we'll draw a line 15 degrees. Then we go back to the star chart, and let's say it says 30 degrees. So we go another 2 segments, or 30 more degrees, and we know we're on that longitude. The one that says 30, that's the longitude we'd be on. Okay, we'll do one more. And on the original Gleason's map, there's the 2 hands that represent longitude and time, and there's latitudes all the way down the hand. So we wouldn't even have to draw lines. But let's say in this example, we get a GHA of 45 degrees and a SHA of 30 degrees. So we'll move the hand 45 degrees off of 0 Greenwich hour angle, and then we'll add 30 degrees to that. So the hand will line up where it says 30 right there, and then whatever your latitude is, that's your exact position on Earth. Okay, that's how it works with the stars. I probably should have used the hands, but I think y'all get the picture. So you see the longitude hand, and you see the latitude lines written all the way down. So you line up the hand with your star's longitude, and then you get the declination or latitude, and you can mark it. And where they cross is the star's exact position over Earth. And you could use the other hand to mark your location. And I'm going to show how to do that with stars in a future episode. So we've showed how to plot the star's exact position above Earth. We've showed how to chart the sun's exact position over Earth. And we've showed that it's impossible to celestial navigate on the surface of a globe for multiple reasons. Despite the fact that you cannot get a 90-degree angle from the surface of a sphere, there's other problems. Look at the 3 positions on Earth at the equator represent 3 different people looking at 3 different places in the sky, but they're seeing the same star. So how can we calculate the same star from three separate positions looking in three separate areas of the sky. We cannot. What they do is they take it down to the center of the Earth for a couple reasons. One, to unify their location, to even justify the fact that they're looking at the same star. And number two, by doing that, they're chopping the Earth in half, effectively giving them a flat plane so they can even have an angle to do the math with. And even that comes with assumptions that the stars are infinite distance away. It's a joke if you ask me. I mean, in my opinion, it's a joke. I don't see how they claim victory with a straight face. Now, I had another thing I thought was interesting I wanted to show you guys. They tell us that the stars are constantly moving, and in 1,000 years, Polaris won't be the North Star or some shit, but they say that I heard it's like a third of a degree every 20 years. So I went to looking at this. So let's check this. So we'll take Aldebaran and look at right there. It says 291, 21.4. This was in 1976. So we go to 1981, and Aldebaran says 290 degrees, 52 minutes. Okay. Then we jump to 2001, and it is 290, 52. So it seemed to change, but then all of a sudden it stayed the same. So now Aldebaran showing 290, 57.6. Oh, wait, it changed again. You jump to 2005, and it's 290, 52. It's back to what it was. 2008, we jumped forward a few years, and it's 290, 52. It's maintaining now. Now 2009, it's, what do you know, 290, 52. So let's jump to 2010, Aldebaran, 290, 52. So it's moody, we'll call it. 2013, 290, 52. Okay, 2014, Aldebaran, 290, 52, 1631 declination. 2016, 290, 52, 1631 declination. Okay, 2020, 2090 or 290, 52 minutes. So it does whatever it wants. 2022, the same, 290, 52. So 2023, oh, wait a minute, 290, 41. So it's in its mood again. It decided to jump. So the point being, I've just showed 40 years between 1981 and 2022 where it didn't change at all. So it's always just processing around. So they're not changing with respect to each other. It's just processing around, which is pretty much what we would expect on a flat Earth. I'm also under the opinion it's not as accurate as they portray. I mean, I do believe it works. It is a useful tool, but I don't think we can navigate within a half, maybe mathematically, but not get within half a mile accurate distance over, thousands of miles. Maybe when we get up close. But I did show that they're just processing, like after 4 decades, man, they're not moving in respect to each other. I will let y'all be the judge of that, and I appreciate it for the people who wrote it out to the end.